Okay, let's start today's seminar. Today's speaker is Bingrong from Cornell University and Korea University. He will talk about the Sphaleron in the Higgs Triplet model. Please start when you're ready.
Great, thanks. Good afternoon, everyone. I'm Bingrong Yu. I'm a postdoc in Cornell University and also a joint postdoc in Korea University. I arrived in Korea 2 weeks ago, and I will spend most of my time here until the August of next year working with Sun. So hopefully I can have more connections with the HEP community in Korea, including all of you. So today I'm very glad to introduce our recent work, which is a study of the electroweak Sphaleron. This work was in collaboration with Jiahang Hu, who is a student in UCAS, and with my PhD supervisor Shun Zhou at IHAB. In this work, we studied the Sphaleron configuration in the Higgs triplet model, which extended the standard model by adding one SU2 triplet scalar. The Sphaleron is a very old topic. The Sphaleron process plays a very important role in dynamically generating the baryogenesis of the universe. The calculation of the Sphaleron is not easy because it is a non-productive process. Nowadays, there are not too many people working in these areas. However, we feel it is a very interesting thing to do such a calculation. Here's my outline. First, I will introduce the motivation of this work. Then I will briefly review the Sphaleron in the standard model. I will introduce the strict definition of the Sphaleron configuration in the standard model and how to calculate the Sphaleron in using a general method. Then we turn to the study of the Sphaleron in the Higgs triplet model. I will show how to derive the equation of motions of Sphaleron in the Higgs triplet model. And then I will show the Sphaleron solution in this model, including the field configuration and the Sphaleron energy. And finally, I will summarize the main conclusion of this work and give some brief comments about the outlook of the future extension of this work, such as electroweak baryogenesis or phase transition in this model. So please feel free to stop me if you have any question at any time. The standard model of particle physics is very successful. However, we know there are some important questions that cannot be answered in the framework of standard model. Two of the most important ones are the arrangement of neutrino masses and the cosmological matter-antimatter asymmetry. We know in the standard model, there is not an explanation for the tiny masses of neutrinos. And in the standard model, there is not a successful electroweak baryogenesis because of two reasons. The first one is that the Higgs in the standard model is too heavy, so the electroweak phase transition in the framework of standard model is a crossover, such that the generated baryogenesis will be washed out, and we cannot explain the baryogenesis which is observed. And another reason is that the CP violation in the quark sector is too small to generate sufficient baryogenesis. Then can we explain both of these two important questions in a unified BSM framework? At a very successful early attempt in the thermal electrogenesis proposed by Fukita and Yanagita in 1986. This is a minima framework that is very successful, which extends the standard model by adding three singular fermions, or so-called right-handed neutrinos. However, in this framework, the natural scale of the new physics is very high, typically at the gut scale. So this is difficult for for us to probe it using the colliders. Alternatively, we can also extend the standard model by adding one complex triplet scalar, which has which is a singular under the color charge and the triplet under SU2L gauge group and carries a non-zero hypercharge. And in this model, which is called the Higgs triplet model or type 2 seesaw model, the breaking of the vacuum of this triplet can actually give the tiny Majorana mass for neutrinos. Here, this Majorana neutrino masses is proportional to the Y data, which is the coupling, and the V data, which is a wave of the triplet. And in this Higgs triplet model, the typical scale of new physics can be much lower compared with thermal electrogenesis, which is typically at TeV scale. So hopefully we can probe it using colliders in the future. Then can the Higgs triplet model also explain the baryon asymmetry of the universe? We have several frameworks to realize it. The first one is triplet electrogenesis. This is very similar to the thermal electrogenesis by singular fermions. In the early universe, the decay of the heavy triplet will explicitly violate the lepton number, and the generated lepton number will partly exchange to the baryon number through the Sphaleron process. However, in this framework, in order to generate non-zero CP violation, so that non-zero lepton number, we need to include at least two different triplet scalars. But to accommodate neutrino masses, we only need one triplet scalar. So this is not a minimal framework to explain the baryon symmetry of the universe. And very recently, there is a work which claimed that the inclusion of only one triplet scalar is enough to generate the observe the baryon symmetry of the universe through the F-like dying mechanism. And at the same time, the triplet scalar can also play a role as an inflaton. However, this is a very interesting work. However, in this framework, we need to assume some non-minimal coupling between the triplet scalar and the graviton. And in this talk, I will mainly focus on a more traditional scenario, which is electroweak baryogenesis. The electroweak baryogenesis in the Higgs triplet model is different from that in the standard model, at least from two aspects. On one hand, the scalar potential of the standard model is extended by the triplet. So the pattern of the electroweak phase transition is modified, and hopefully we can have a strong first order phase transition in this model. On the other hand, there are new sources of CP violation, which comes from the coupling between the triplet and the lepton doublet. So there will be more CP asymmetries propagated through the bubble. So then the question is, can we have successful electroweak baryogenesis in the framework of the Higgs triplet model? If the answer is yes, then that will be great, because we can explain both the neutrino masses and the baryon symmetry of the universe in a very minimal framework. However, up to now, the answer to this question is still not clear in the literature. And in order to answer this question, the first step is to calculate the Sphaleron configuration in the presence of the triplet. So this is a main motivation of our work. Okay, is there any questions up to now? Okay, great. Let me first briefly review the Sphaleron configuration in the standard model. We know that the vacuum structure of a general non-abelian gauge series is non-trivial, and the vacuum can be distinct by some topological numbers, which are integers. Sorry, called the Chern-Simons numbers, NCS. The Chern-Simons numbers are the functional of the gauge fields, and also depends on the gauge coupling G. So this is a naive picture of the field configuration in the nonlinear gauge field series. That the field configuration depends on the energy and the Chern-Simons numbers. So you can see here that for this deepest point, they have the same energy, but are characterized by different Chern-Simons numbers because they are topologically different. And because of the chiral anomaly in gauge series, the baryon number and the lepton number are not conserved, and the exchange of baryon and lepton number are connected to the exchange of Chern-Simons numbers. Here, this NF is number of generation of fermions, and the exchange between topologically different vacuum is propagated by the so-called Insterton process. However, at zero temperature, the Insterton rate is through different vacuum is highly suppressed, about 10 to minus 160. So it's totally negligible at zero temperature. Another choice to propagate the baryon symmetry and lepton number symmetry is to get over the barrier through the Sphaleron process. The Sphaleron configuration is defined as the saddle point of the energy functional, which is defined on this manifold. And we can see here the highest point through this direction, which corresponds to the non-integer, the half integers of Chern-Simons numbers are the configuration of Sphaleron. I will give a more strict definition of Sphaleron later. Therefore, the rate of the baryon number violating process is determined by the Sphaleron transition rate. And at zero temperature, the Sphaleron energy, which corresponds to the height of this energy barrier, is proportional to the wave of electroweak symmetry breaking, and its typically scale is around 5 TeV. And at a low temperature, the Sphaleron rate is exponentially suppressed, while at a high temperature, the Sphaleron rate is very sufficient and is not suppressed. Okay, then let me give a more strict definition to the Sphaleron configuration. So first, this name of the term of Sphaleron comes from some Greek letters. It has the meaning of unstable or ready to fall. So you will see why it has such a meaning. So first, we define N to be the configuration space of all of the static fields with some boundary conditions and finite energies. And on this configuration space M, which is manifold, we can define all of the fields, which include the gauge fields, the scalar fields, and so on. And also on M, we can calculate the total energy of this system, which is functional, defined on this space. And then the Sphaleron configuration is defined as the saddle point solution of the energy functional. Here, the saddle point means it is the largest value from one direction, but it is a minima value from another direction. So it is not a local minima and not a local maxima, but a saddle point. Then what's the general strategy to search for the saddle point or to find the Sphaleron solution? It is called the min-max procedure. So the general strategy is as below. The first step is to construct a set of non-contractible loops called CI, which connect different vacuum. Here, the non-contractible loops means loops which start and end at the vacuum, but they cannot be continuously deformed to one point. So this is the meaning of non-contractible. And the second step is to, on each loop, we find a certain configuration which has a maxima energy denoted by Ci max. And the final step is to minimize all of these maximum value over all of the loops. So then this gives the configuration of the Sphaleron according to the definition. So here is a very simple example, a simple but non-trivial example. Consider a two-dimensional torus, which is put on the reference plane, and the height from the plane is a function which defined on this torus, right? And according to a famous topological identity, the number of the minima on this torus and the number of saddle points and number of maxima can be connected to each other with topological character of this manifold. So for the genus can be intuitively understood as the number of holes inside this manifold. So for the torus, the genus is 1. So the number of minima minus number of saddle point plus number of maxima is 0. So we can check it quickly because we have two minima and two local minima. We have one local minima and two saddle points and one local maxima. So this indeed vanishes. Then how to use the min-max procedure to find the saddle point? That is to first start a set of non-contractible loops which start from P naught, because P naught is the local minima of the height, which corresponds to the minima energy point, that is a vacuum point. And all of these non-contractible loops should start and end at P naught. And for every loop, there is a maximum height. There's a point which has a maximum height, which is at here. Then you include all of these set of non-contractible loops and find the minima one of the maximum height, which is pointed here. It's P1. So this corresponds to the saddle point, and it is the Sphaleron configuration we are looking for.
I have a question.
Okay.
Can you tell me a bit more about why the Sphaleron configuration is the center point of the energy function?
Okay, so you know the vacuum is minima of energy, right?
Right.
And it's stable. But the Sphaleron configuration is defined to be an unstable point. So the first derivative is 0, but the second derivative is not. So it's not a stable point, but it's an unstable point, which corresponds to the saddle point in geometry. And you can refer to the picture here. So along this side, the Sphaleron is the maximum point, right? But along this side, another side, it's a minima point. So this is corresponds to the saddle point.
Okay.
Sorry, so in this, so the loop you said, so how can we write the loops in this?
You mean in this question?
Yeah, in this.
Yeah, this is a very non-trivial thing to do in calculating the Sphaleron. That is how to explicitly construct the non-contractible loops, right? There's not a general procedure to do such a thing, but we can I mean, for some certain problems, we can explicitly write down some non-contractible loops. Then you can verify that they are indeed non-contractible and they provide the saddle point solutions. I will show the example later.
So the loop you mean is the loop in the configuration space.
Yes,
Is that
the loop in the configuration space, and which is infinite dimensional space.
okay. Which connect different vacuum. Right.
Yes.
So on the next slide, the P2 point is also a Sphaleron, right?
Yeah, it's also a set point.
But it doesn't satisfy, you can't find it with this algorithm, or you can?
Yeah, you are correct. This min-max procedure does not guarantee that you can find out all.
You just
of
find
the,
a set.
Yeah, you cannot guarantee that you can find all of the set points.
Okay.
Great. Although I will not talk too much about mathematics, but there are some very basic introduction about the topology, which is a concept of homotopy and homotopy groups that are will be useful in calculating the Sphaleron. So intuitively, the two passes we call they are homotopic to each other, which means you can transform one pass continuously to make it to be identified with another one, and this is more precise mathematical definition. So you can see that the two passes which start and end at the same points, they can be continuously deformed from one to another, so they are homotopic to each other. And in particular, if the path, the starting point and the ending point of the path are identical, then we call such a path a loop. And you can prove that all of the loops that are homotopic to each other will form a group. It's called the homotopy group. This is the group defined on the manifold N. And for the definition of a one-dimensional object mapped from it to a general manifold, this homotopy group is called the fundamental group, or the first homotopy group, denoted by pi1m. This is a very simple example. Think about the fundamental group defined on R2. So you can see this is trivial because in a plane, when you write some loops, you can continuously transform it to a single point. So all of the loops in this homotopy class are identical to one point. So this is trivial. That is why the homotopy group defined on R2 is 0, is trivial. However, if you take off the 1 point in the plane, that is quite different, because when you draw some loops which include this removed point, then you move one cycle, 2 cycles, or n cycles. They are topologically different, right? So this is why the homotopy group defined on this manifold is non-trivial, and it's the integer group. And this definition of the homotopy group can be easily generalized to higher dimension. In particular, for n-dimensional loops which induce a map from Sn to n, we can define the corresponding n-dimensional homotopy group, which is denoted by pi n m. And for later, we will see that the m in the calculation of Sphaleron is actually SU2. So which is equivalent to S3. Okay, and n is equal to 2 or 3. depending on the unitary transformation you will use. So it will be pi to 3 or this will be only homotopy groups we will use later. Okay, there are any questions to the contents? Okay, now let's turn to the study of the Sphaleron in the Higgs triplet model. So first, we make two assumptions. We will neglect the contributions from Fermi fields. That means we only include the interaction of scalar fields and the gauge fields. And the second assumption that we neglect the mixing between SU2L and UY1. This will lead the solution of the Sphaleron to have a spherical symmetry. And the inclusion of the finite Weinberg angle will slightly modify the Sphaleron energy, but the influence is very small. It's at the order of about 1%. So we can safely neglect it. Then we write down the Lagrangian in the Higgs triplet model, which includes the kinetic term of gauge fields of doublet scalar, triplet scalar, and the scalar potential. And from the Lagrangian, we can have the total energy of this system, which is functional of gauge fields and doublet and triplet scalars defined on the field configuration space. Okay. As I said before, the key point to find the Sphaleron solution is to construct the non-controllable loops. Then how do we construct it? We can first start from the vacuum configuration. That is, the vacuum configuration of gauge fields of doublet scalar, triplet scalar can be constructed as this form. So this is easy to verify, right? Because the first identity corresponds to the pure gauge, which means the field strength vanishes at the infinity. And the second identity comes from the fact that the Higgs doublet follows fundamental representation of an SU2 gauge group. And the second identity comes from the triplet scalar transformed as a joint representation of SU2 gauge group. Okay, so here the U infinity, which has two arguments theta and phi, is a general unitary transformation that guaranteeing the polar gauge, and it defines a map from S2 to S3 because the arguments is you have two arguments theta and phi, so the space of arguments is S2, and because it's SU2 unitary group, so the value from a space of S3. So it's a defined map from S2 to S3. And this map corresponds to the contractible loops. This is because the homotopy group of pi2 of S3 is trivial, it's identity. And in physics, this corresponds to the fact that the fields at infinity can be continuously transformed to the vacuum configuration. So you can see this is the usual vacuum configuration if you choose one gauge, and this is a vacuum configuration. And because this is continuous transformation, so that means fields at infinity can be continuously transformed to the vacuum. But this is not what we are looking for to find the Sphaleron configuration. Then in order to construct the non-contractible loops, we need to introduce one additional parameter called mu. And we can explicitly construct the unitary transformation matrix, which now has 3 arguments, mu, theta, and phi. The mu parameter is in the range of 0 to pi, and when it takes the value of 0 and pi, you can check that this gives the identity transformation. So this corresponds to the vacuum configuration. So this means the start point and the end point corresponds to the vacuum. And when mu varies from 0 to pi, it will parameterize the loop from one vacuum to another vacuum. Then you can verify that this transformation defines a map from S3 to S3. And because of the homotopy group of pi 3 of S3 is non-trivial, it's different, it's topologically different depending on how many loops you have. So this means such loops constructed from this matrix are indeed non-controllable loops. Then using the constructed non-controllable loops from this matrix, we can write down the Sphaleron answers compared to the vacuum configuration. That is simply to replace this U infinity with this more general U. And here, FR, HR, and H delta R are 3 profile functions to be determined by some other conditions. Okay, so in addition, in order to guarantee the gauge symmetry, we will ask the profile functions to satisfy the boundary conditions. That is, they should vanish at the orange, and their value should be the unity at infinity, which means they cannot be some very steep functions. Then we can use min-max procedure, as I said before, because now you have the expression of all of the gauge fields and the scalar fields. Then you simply substitute them back to this energy functional, and now the energy is the function of one parameter mu. And you calculate the first derivative and second derivative of the energy with respect to mu. And you can explicitly check that when mu equals 0, pi, or pi over 2, the first derivative vanishes, which means these 3 points are all stationary points. However, when you calculate the second derivative, you find that mu equals 0, mu equals pi. The second derivative is positive, which means the energy is local minima corresponding to the vacuum configuration. While when mu equals pi over 2, the second derivative is always negative, which means the energy is local maxima in the loop. So this corresponds to the Sphaleron configuration, what we are looking for.
So you can prove these equations by using the equation of motion, or
no, we haven't using the equation of motion. We just simply substitute these expressions back to the definition of energy functional. Then you perform the variation with respect to mu, and you can prove it's always positive, negative when mu.
It's a bit surprising that you are saying that for any function f, h, and h delta.
Yes.
So you can.
Yeah. This can be checked explicitly. Yeah. Okay. Okay. Now, because we have already know that mu equals pi over 2 corresponds to the Sphaleron configuration. So we take mu equals pi over 2 in the expression of fields, and now each terms can be written down explicitly. We can see that the kinetic terms of gauge fields and the doublet scalar is very simple, and it's almost the same as the case of standard model, which has a spherical symmetry. While the kinetic terms of the triplet scalar is a little different from the previous terms, because it depends on theta, which means it is not spherically symmetry. This is because the triplet follows a more complicated representation, that is a joint representation, not the fundamental representation of SU2 gauge group. And the scalar potential in the Higgs triplet model, this is most general form. So the most general gauge invariant terms in the scalar potential, including one doublet and one triplet. So there are totally 8 real parameters in the scalar potential. But later we will see that not all of them will participate in the Sphaleron configuration, which means not all of the parameters in the scalar potential have connection with the baryon symmetry process.
So this is a zero temperature potential. So
yes, this is zero temperature.
You also consider beneath temperature effects?
In principle, we should include the temperature effects, and I will talk later. But in these calculations, we didn't include the final temperature effects. Okay. And we also didn't include the one loop correction to the effective potential. This is a tree-level zero temperature potential. Okay. And the waves of the doublet and triplet can be determined from minimizing the scalar potential. Okay. Now it's time to calculate the Sphaleron energy. We can substitute all of the previous terms into the energy functional, and we obtain the expression of the Sphaleron energy. Here we have defined a dimensionless quantity C, which is used to characterize the typical scale of a Sphaleron. And we can see that the Sphaleron energy and the Sphaleron configuration in the Higgs triplet model only depends on 5 independent parameters from rho 1 to rho 5. So here rho 1 is the parameter proportional to the quartic coupling of the doublet scalar, and rho 2 is connected to the trilinear interaction between doublet and the triplet, and the rho 3 is defined as a ratio between 2 waves, and rho 4 is proportional to kappa square, which is quadratic coupling of the doublet, and finally rho 5 is a parameter of the triplet mass. Okay, then you do you perform the derivative of the Sphaleron energy with respect to the parameter C. And then, it's with respect to the profile functions f(h) and h'. Then you obtain 3 second-order differential equations. They are the equations of motions of the Sphaleron configuration, right? So this step corresponds to you minimize all of the maximum values over all loops. So this corresponds to the definition of saddle point, which is the Sphaleron configuration. And these are 3 coupled nonlinear second-order differential equations with respect to C, together with the boundary conditions of f(h) and h'. And they are not easy to solve. And in our paper, we developed the spectral method, which can be used to solve these 3 coupled differential equations. I will not talk too much in this talk because it's only a mathematical method that can be efficiently used to to solve the differential equations. And when you obtain the solutions of all of the profile functions, you can simply substitute them back to this expression and perform the integral. Then you obtain the energy, the value of the Sphaleron energy, which should be some multiplies to this 4 pi v over T. Okay. So before I show the solution of the Sphaleron configuration, is there any questions now? Okay. In principle, for any values of these parameters, the differential equations can always be solved using the spectral method. But we know that all of the parameters have some physical meanings, so they cannot be taken to arbitrary values because there are some constraints from both theoretical and experimental aspects we need to consider. The most strict constraint comes from the electroweak precision measurements on the triplet wave. So because this triplet wave violates the custodial symmetry of the electroweak theory, so they cannot be too large, then the rho 3 parameter, which is defined as a wave ratio, has an upper bound about 10 to minus 3. In addition, the rho 4 parameter can be expressed using other 4 parameters as a good approximation. Apart from this, there are some other constraints which include the bounded from below conditions and the unitarity conditions in the scalar potential. That means couplings in the scalar potential can neither be too large nor too small. And in addition, we need to reproduce a neutral CP even scalar, which has a mass around 125 GeV in the scalar spectral. This gives also a constraint on these parameters. And the collider search for doubly charged of Higgs set a lower bound to the mass of the doubly charged Higgs, which is around 350 GeV. So, which means the parameters should satisfy this condition. And because the interaction of the triplet and the doublet and the lepton doublet violates the lepton number explicitly, so it can induce the charged lepton violation process like the mu case to E gamma. And the experimental search for such charged lepton flare violation process has no signals which set a lower bound on the triplet mass, on the product of triplet mass and the triplet bar. Okay, so all of the constraints on this page, will put some strict bounds on these low parameters. Okay, now let's show the solution of the Sphaleron field configuration. In the first 3 figures, we show the evolution of the profile functions fh and h hat with respect to C. And in the last figure, we show the energy density of the Sphaleron with respect to C. And we can see that all of these 4 figures, the Sphaleron configuration is restricted within a very narrow range. Typically, the C should be less than about 10, which corresponds to R smaller than about 10 to minus 15 centimeter. So this is even 2 orders of magnitude smaller than the length scale of a proton. This is why the Sphaleron looks like a particle which is localized near the orange. and because the length scale of the Sphaleron is about 2 orders of magnitude smaller than the proton, the volume is 10 to -6 smaller than the proton. And because the typical energy of the Sphaleron is about the order of 10 TeV, so the energy density of the Sphaleron, if you look at it as a particle, the energy density is about 10 to 10 of the energy density of proton. Then the interesting question is that can we produce electroweak Sphaleron using high energy colliders? We can make a simple estimation because the typical energy of the Sphaleron is about 10 TeV, which means the energy density of the things. It's about 10 to 10 times the energy density of the proton. Then we consider the largest energy of LHC and take it to be around 10 TeV. So for a moving proton which has an energy of 10 TeV, its energy density, I mean the energy density of protons at LHC is about 10 to 4 times 10 to 4 times proton times the energy density of a static proton, right? This 10 to 4 is because the energy of the LHC proton is about 10 about this multiplies mass of the static proton, and this comes from the Lorentz contraction, because for a moving proton, the length in the moving direction is contracted by relativity effect, right? So even the largest LHC proton, it's still be 2 orders of magnitude smaller than the energy density of the Sphaleron. So it's still impossible for high energy collider to produce a Sphaleron configuration. However, if you interesting in that, if you include the strong magnetic fields, the probability to generate the Sphaleron at collider will be enhanced. This is because when you take into account the effect of finite Weinberg angle, the Sphaleron configuration will not be spherically symmetric. But it will have some certain directions, which means the Sphaleron will has nonzero magnetic dipole moment. Then if you put the strong external magnetic field, this will significantly reduce the energy of Sphaleron. So that will enhance the probability to generate a Sphaleron. However, this strong field, strong magnetic field is not available currently. So unfortunately, we have no practical method to produce Sphaleron in the collider at current. Okay. Now we take a look at the this parameter, which is proportional to the trilinear coupling between the doublet and the triplet. You can see from these 4 figures that if we enlarge the ρ2 parameter, all of the profile functions will tend to the vacuum configuration more slowly. In addition, a larger trilinear coupling will diffuse the distribution of the Sphaleron energy and decrease the total energy of the Sphaleron. Okay. Now we show the Sphaleron energy in terms of the row 2 and row 5 parameter. And we keep the row 3, to, which is the web ratio, to be its upper bound. And the row 4 can be calculated using other 4 parameters as a good approximation. So we can see that in the standard model, the row 1 parameter is completely fixed by the mass of Higgs boson and the wave. So in the standard model, the energy of the Sphaleron is also completely fixed. It's about 90 eV. However, in the Higgs triplet model, when you change the value of values of row 2 and row 5, we find that the Sphaleron energy is significantly changed compared with the Sphaleron energy in the standard model. We find a larger trilinear coupling or a heavier triplet scalar will correspond to a smaller Sphaleron energy. And as I said, the row 1 parameter in the standard model is completely fixed by the Higgs mass. But in the Higgs triplet model, the row 1 parameter is not fixed because you have more parameters in the scalar potential. So in these figures, we exchange the value of row 1 and row 2 and show the behavior of the density plot of the behavior of the Sphaleron energy. And we find the interesting thing that when row 1 becomes larger than its standard model value, the variable parameter space began to split into 2 regions, two distinct regions. We call the region 1 and region B. In region 1, in region A, it corresponds to larger trilinear coupling and heavier triplet scalar. Typically, the triplet scalar is heavier than about 1 TeV. While in region B, it corresponds to much smaller trilinear coupling and lighter triplet. The triplet should be typically lighter than about 1 TeV. And in this region B, the allowed region is restricted into a very narrow bounds, which can be tested by future collider searches. And we find the Sphaleron energy in region A and in region B are reside in this region. So our conclusion that the allowed Sphaleron energy in the Higgs triplet model can be enhanced up to about 30% compared with the standard model case. This corresponds to that the baryogenesis in the Higgs triplet model is more difficult to be washed out by the inverse process of Sphaleron. This is because inside of the bubble, the baryogenesis will transfer from the symmetric phase into the broken phase. And the Sphaleron transition rate is depend on the exponential of its energy divided by temperature. So inside the bubble, we have a larger Sphaleron energy compared with the standard model, which means we have a smaller Sphaleron rate. So this means it's more difficult for the generated baryogenesis to be washed out by the inverse process of Sphaleron. So this is what we want when we do a successful electroweak baryogenesis. Okay. Okay. Are there any questions?
In those regions, like, did you? I mean, did you look at the phase transition? Whether it's first order and?
We haven't looked at the phase transition. These regions are only allowed by by these constraints.
I see. Because like eventually you want
Yes.
to look for it to
Yeah.
value it.
Eventually, if you include the loop corrections and the final temperature effects, and you want to perform a successful baryogenesis, you need to look at the long region for first order consideration. Yeah.
Is the washout inside the bubble from Sphaleron processes a serious concern in electroweak baryogenesis?
Sorry?
You said that it's more difficult to wash out the asymmetry.
Yeah.
Is it a big problem usually in electroweak baryogenesis?
Because in the standard model, you know, the spiral rate inside the bubble is larger than the Hubble expansion rate, right? So this is not a first order phase transition, which means the barrel symmetry will be washed out. And in a BSM model, in general, you can have a spiral rate that is smaller than the standard model case. So the barrel symmetry can be guaranteed. Okay.
Well, the Sphaleron anyway can't destroy B minus L, right?
Yes.
So I don't know what you exactly mean by washout.
Washout, I mean, because of the existence of CP asymmetry, the collision between the particles and the bubble walls will transfer barrel symmetries inside the bubble, right?
Mm-hmm.
And the spiral rate outside the bubble is very significant because this is high temperature.
It's T to the 4, right?
Yeah. So it's in thermal equilibrium. And if the spiral rate inside the bubble is also in thermal equilibrium, then the inverse process of spiral will wash out the generated barrel symmetry. So we require the spiral rate inside the bubble to be smaller than the bubble expansion rate, which means it's a departure from thermal equilibrium. And now, if we have a larger spiral energy, which means we have a smaller transition rate, then this condition is easier to be satisfied.
So my question is, in like a normal model, without a Higgs triplet, just some singlet scalar, what kind of washout? How much is usually washed out of the generated asymmetry?
It depends on your parameters.
How much can it be a lot, or is this?
It can be completely washed out in some regions. Because in a general model, when you exchange when you adjust the parameters, the spiral energy can be larger or smaller than the standard model case. Thanks. Okay, then let me make a summary. So the Higgs triplet model is hopefully to provide a unified framework to explain both the neutrino masses and the barrel symmetry. And in order to do a complete electroweak baryogenesis in this framework, we calculate the Sphaleron configuration in this model as a necessary step. And we find that the Sphaleron configuration in the Higgs triplet model in general depends only on 5 parameters from rho 1 to rho 5. And we find that the quality coupling parameter rho 1 will increase the Sphaleron energy, while the trilinear coupling rho 2, the wave ratio parameter rho 3, and the triplet mass parameter rho 5 will in general decrease the Sphaleron energy. And basically, because of the constraints from electroweak precision measurements, the difference between the spiral energy between the Higgs triplet model and the standard model will be highly suppressed by this small triplet wave. However, we find that there still exists some narrow parameter space that the spiral energy can be enhanced up to about 30% compared with the standard model case. And such a narrow space is possible to be tested by future collider searches. Okay, finally, I would like to make some brief remarks on the possible future extensions along this work. The first one is to take into account the finite temperature effects of the calculations above is based on the zero temperature field theory. If you want to include the temperature effects, we need to calculate the scalar potential and the wave and the Sphaleron configuration, including the temperature corrections. And the point is that the wave ratio parameter rho 3 is not suppressed by experiments when you're taking into account the temperature effects, which means it can be much larger than the vacuum value. And in this plot, we show the behavior of the Sphaleron energy with the rho 3 parameter. And we find for a much larger rho 3, the Sphaleron energy can be significantly decreased compared with vacuum case. Okay. And another possibility is to consider the two-step phase transition. In the two-step phase transition scenario, and at the end of the first step, the wave of the triplet can be much larger than the wave of the doublet, which means it can lead to a more significant corrections to the Sphaleron energy compared with the standard mode case. Okay, another interesting investigation is to look at the effects of leptonic CP violation or electroweak baryogenesis. We know in the standard model, because the neutrinos are massless, so there's no flavor mixing in the leptonic sector, and the only sources of CP violation comes from the quark sector, but it is too small to explain the baryon asymmetry. And in general BSM scenarios, there can be new sources of CP violation. And in the Higgs triplet model, because of the coupling between the triplet scalar and the lepton doublet, this term will violate the lepton number and induce new sources of CP violation. And such CP violation can be directly measured in the long baseline neutrino experiments, neutrino oscillation experiments. So hopefully this new source of CP violation will be transferred between the collision in the collision between the triplet and the bubble wall, and this can cause sizable effects during the baryogenesis process. Okay, so much for today's talk. Thank you very much.
Thank you very much for the nice talk. Any further question?
So can you also consider dark matter candidate in this model? About neutral component?
Unfortunately, the neutral component cannot be the candidate of dark matter in this model because it has a nonzero hypercharge.
Okay.
Yeah. There is another kind of model which you include the also a triplet, but it's a real triplet with zero hypercharge. And in this model, the neutral component of the triplet can be a candidate of dark matter. This is also a well-studied model, but it cannot generate the neutrino masses.
But can you make it a portal to the dark matter if you couple this triplet to?
Yeah, this can be possible. Yeah, or you can include both real triplet and complex triplet, cause GM model. And in this case, you can both have the neutrino masses and the dark matter candidate and keep the custodial symmetry at the true level. Okay.
How about collider searches for this kind of trilinear couplings between the material?
Yes, there are now very strict constraints from collider search, but it's mainly on the search for doubly charged Higgs and singly charged Higgs.
Mm-hmm.
And you can see that it also depends on the the O2 parameter, which is trilinear coupling. So I mean, it can only put a lower bound on the doubly charged Higgs mass, and it can indirectly also put some constraints on this trilinear parameter, but not a direct constraint.
Yes. So I think really you need to compute this condition for the first phase.
Yeah, there's already some work on which started also a very recent work in the March of last year, which studied the gravitational waves and the first order phase transition in this model, and they find there is some variable space for strong first order phase transition, but they didn't study the Sphaleron or the baryogenesis.
Yeah, because if you overlap these two studies, then you will define the parameter space where you baryogenesis work. Then look at this trilinear coupling, then maybe you see this must be explored in the high lumiere HC or not. You can say.
Yeah, exactly.
Any other question? Okay, if not, let's thank Spear again. Thank you very much.